Hello students, I hope you are fine and doing well in your studies. Students, today we are going to start from where we have finished in the previous class. In this session, we will study the basic fundamental of this chapter and we will do some basic example also. So students, let's start with the chapter itself. Students, now we are going to study representation of a complex number. First is the geometrical representation. The complex number z is equal to x plus iota y can be associated with the ordered pair x comma y. We consider two perpendicular lines OX and OY analogous to the Cartesian system called as the real axis and imaginary axis respectively, and where O denotes the origin of reference. The resulting plane is called as the Argand plane or Gaussian plane or complex plane, and Z is represented by the point P corresponding to the ordered pair x comma y. The point P is called as fx of Z. It is the imaginary axis, it is the real axis, and this point P represent the fx of a complex number z, where z is equal to x plus iota y and it is the origin, and this length means OP length is denote the modulus of the complex number, and this angle Q is denotes the argument of the complex number. Students, second representation is the polar form or trigonometric form of a complex number. In this form, let z is equal to x plus iota y, and according to the diagram you can say that it is the real axis, it is the imaginary axis, and point P is here, and this is the representation of a complex number z. Length OP is the modulus and it is represented by r. This angle is the argument theta. We are going to draw the perpendicular here. This length is x and this length is y. You can write this is the point M. Now according to this diagram you can say x is equal to r cos theta and y is equal to r sin theta. Then complex number z is equal to x plus iota y can be written as r cos theta plus iota r sin theta, just like here. Now r is a common factor and it is equal to cos theta plus iota sin theta, where theta is the argument. This is known as the trigonometric or polar form of a complex number. Here we would take the principal values of theta. For general values of the argument, complex number can be written as r cos 2n pi plus theta plus iota sin 2n pi plus theta, where n is an integer. Sometimes cos theta plus iota sin theta in short is written as cis theta. This is the polar representation of a complex number. For example, if z is equal to 1 plus iota, then we have to find the modulus, means mod z, this is equal to root 2, and theta, that is the principal argument, and it is equal to pi by 4. Then we can write complex number z as mod z into e to power iota theta, or you can say it is mod z cos theta plus iota sin theta. This form is called the exponential form. It is next form, and here it is the polar form, and in the polar form we can write it is a root 2 times cos pi by 4 plus iota sin pi by 4. This is the representation of a complex number in the polar form or trigonometric form. Now here is the exponential form of a complex number, or we can say Euler's form. According to the Euler's theorem, e to power iota theta is equal to cos theta plus iota sin theta, and this setup is studied in the trigonometric form, and it is equal to e to power iota theta, and therefore z is equal to r cos theta plus iota sin theta can be written as z is equal to r e to power iota theta, which is called as exponential form of a complex number. Replacing theta by minus theta in e to power iota theta, we can obtain e to power minus iota theta is equal to cos theta minus iota sin theta, and this is the representation of z bar. If this is z, then z bar is represented by e to power minus iota theta, and this form is called the exponential form or Euler's form of a complex number. So student, as we know, e to power iota theta is equal to cos theta plus iota sin theta, and e to power minus iota theta is equal to cos theta minus iota sin theta. Now if we add these two equations, then we can find 2 cos theta is equal to e to power iota theta plus e to power minus iota theta. That's why you can find cos theta is equal to e to power iota theta plus e to power minus iota theta upon 2. And after simplification, you can also find it is equal to x upon under root x square plus y square. Similarly, sin theta is equal to e to power iota theta minus e to power minus iota theta upon 2 iota, and it is equal to y upon under root x square plus y square. Students, here let's we see one example. Write the following complex number in polar and exponential form. Question number 1 is minus 1 by 2 minus root 3 by 2 iota. First of all, we are going to write down in polar form. What is the modulus of the complex number? Means mod z is equal to under root real part is square, it is 1 by 4, plus imaginary part is square, it is root 3 by 4, it is 4 upon 4, within a square root, it is 1. This is the modulus of the complex number. Now what is the argument of the complex number? First of all, we have to find tan theta, and tan theta is root 3 upon 1. It is equal to root 3, means you can find theta, it is equal to pi by 3. As we know, this complex number lies in the third quadrant, means x and y both are negative. So argument of z is equal to minus pi plus theta, and it is equal to minus 2 pi by 3. So we can write the complex number minus 1 by 2 minus root 3 by 2 iota is equal to 1 cos theta, means cos minus 2 pi by 3 plus iota sin theta, and it is sin minus 2 pi by 3. This is the polar form of the complex number, and you can write it is equal to 1 e to power iota theta, and theta is minus 2 pi by 3, so it is minus iota into 2 pi by 3. This is called the exponential form. Okay. Question number 2, 1 minus iota. We have to find the modulus of the 1 minus iota. It is root 2. Now we are going to find argument of this complex number. For the argument, first of all, we have to find the tan theta. Tan theta is equal to mod of minus 1 upon 1 is equal to 1. That's why theta is equal to pi by 4. And as we know, this complex number lies in the fourth quadrant. That's why argument z is equal to minus pi by 4. Now we can write complex number z into the polar form. It will be root 2, it is r, cos theta means cos minus pi by 4, plus iota sin theta, it is sin minus pi by 4. And we can write in exponential form like r e to power iota theta, it is minus iota pi by 4. This is the exponential form of 1 minus iota. Students, here is the vector representation of a complex number. A complex number z is equal to x plus iota y can be represented by the position vector OP of the point P x comma y in a two-dimensional plane. Because the complex number depends on two things. First, its modulus, and second, its argument, which are also the requirement of a vector on a plane. That's why we can represent a complex number as a vector. In this figure, complex number z is equal to x plus iota y is denoted as the vector form, means vector OP represent the complex number Z here. Students, now we are going to study modulus of a complex number. The modulus of a complex number Z is equal to x plus iota y is defined as mod Z, it is equal to within a square root x square plus y square, or you can say it is equal to real Z whole square plus imaginary Z whole square within a square root. In other way, distance of a complex number Z from origin while represented on argand plane is called as the modulus of a complex number, denoted by mod Z, or it is equal to this or small r. Means this OP length, this point is O, this is P, this OP length is equal to R, and it is equal to under root x square plus y square, and it is denoted by mod Z, and it is also called absolute values of Z. Students, one thing must be noted that Z1 minus Z2 is the distance between Z1 and Z2. Means suppose on the argand plane, this is the point Z1 and this is the point Z2, then mod of Z1 minus Z2 represent the length AB. This is one of the most important thing. Student, let's see property of the modulus. As we know, modulus of a complex number x plus iota y is equal to within a square root x square plus y square. So we can say mod z is greater than equal to 0. If mod z is 0, then it is possible only when real and imaginary part both are equal to 0. Property number 2, within a mod z1 into z2 means it is the mod of two complex number and it is equal to mod z1 into mod z2. And in general form, you can say if there are n complex number and they are multiplied with each other, then mod of these multiplication can be converted modulus of product of n complex number is equal to product of individual mod of given complex numbers. Means z1 into z2 into zn whole mod is equal to mod z1 mod z2 mod zn. Now we are going to prove it. Let z1 is equal to r1 e to power iota theta 1, it is the exponential form, and z2 is equal to r2 e to power iota theta 2. What is the value of z1 into z2? It is equal to r1 into r2 e to power iota theta 1 into e to power iota theta 2. Now simplify it. It is r1 into r2 e to power iota theta 1 plus theta 2. This is a complex number z1 into z2. We can easily find the mod of z1 into z2 and it is equal to r1 into r2. What is the r1? r1 is the mod of z1 and r2 is the mod of z2. So we can write here mod of z1 into z2 is equal to mod z1 into mod z2. Property number 3 is this: mod of z1 upon z2 is equal to mod z1 upon mod z2. We can prove it. Let z1 is equal to r1 e to power iota theta 1 and z2 is equal to r2 e to power iota theta 2 like this. Okay, now we are going to find z1 upon z2. What is the value of z1 upon z2? It is r1 e to power iota theta 1 whole upon r2 e to power iota theta 2. Now simplify it. It is r1 upon r2 e to power iota theta 1 minus theta 2. This is the complex number. Now we can find modulus of this complex number z1 upon z2 and it is equal to r1 upon r2. What is the r1? It is the mod z1. And what is the r2? It is the mod z2. So we can easily say that
modulus of the z1 upon z2 is equal to mod of z1 upon mod of z2, and given that z2 is not equal to 0. Property number 4 is here. Mod of z is equal to mod of z bar is equal to mod of minus z, and it is equal to minus z bar mod. Let z is equal to x plus iota y. Then what is the z bar? Z bar will be x minus iota y. What is the minus z? Minus z is minus x minus iota y. And what is the minus z bar? It is minus x plus iota y. And we can find the modulus of all these complex number. In the case of z bar, mod is equal to within a square root a real part square plus imaginary part square. What is the mod z? Mod z is equal to within a square root real part square plus imaginary part square. What is the mod of minus z? It is equal to within a square root a real part whole square plus imaginary part whole square. And what is the mod of minus z bar? It is also equal to real part whole square plus imaginary part whole square. And you can find all these are equal to within a square root x square plus y square, means we can say property 4 is valid. Property number 5, z bar. Let z is equal to x plus iota y and z bar is x minus iota y. We can easily find z bar. It is x plus iota y into x minus iota y. It is equal to x square plus y square, and we can write it is equal to mod z whole square. This is one of the most important property, that z bar is equal to mod z square. Property number 6 is here. Real part of any complex number lies between minus mod z to mod z, and similarly imaginary part of any complex number lies between minus mod z to mod z. Let example z is equal to 3 plus 4 iota. What is the real part of this complex number? It is 3. And what is the imaginary part of this complex number? It is 4. And what is the value of mod of z? It is 5. You can easily observe that 3 lies between minus 5 to 5, isn't it? And 4 lies between minus 5 to 5. That's why we can say properties number 6 is valid. Property number 7, z to power n whole mod is equal to mod z whole power n. This is one of the most important property, and we can prove by using, or you can say by taking any complex number and their power. Let there is a complex number z is equal to 3 plus 4 iota. Then we are going to find 3 plus 4 iota whole square. It is equal to 9 minus 16 plus 24 iota. Now simplify it. It is minus 7 plus 24 iota. This is the z to power n. And now we are going to find the mod of z to power n, and it is equal to within a square root minus 7 whole square plus 24 whole square, and it is 49 plus 576. And now we are going to solve it. It is 625 within a square root, and it is equal to 25. Here z is the 3 plus 4 iota. Now take the mod of z. The mod of z is 5, and here n is equal to 2. Then we are going to find mod z whole square is equal to 25. Now you can say mod z square is equal to mod z whole square. What it means, you can generalize it for this property for any numbers. That's why here property number 7 is mentioned, and it is z to power n mod is equal to mod z whole power n. Property number 8 is here, z1 plus z2 mod whole square is equal to, and this is the final result of this property. And how it is come? Because as we know, z bar is equal to mod z square. That's why we can write it is z into z bar. And z bar is separated out. It is the z1 bar plus z2 bar. Now we are going to multiply these two brackets and we can find this. And as we know, z1 z2 bar and z2 z1 bar means these two system club and make the system like two real z1 z2 bar, and z1 z1 bar is equal to mod z1 square and z2 z2 bar is equal to mod z2 square. So we can write z1 plus z2 square is equal to this. This is the property number 8 here. Now property number 9 is similar. It is z1 minus z2 whole square. By the using property, it is z1 minus z2 into z1 bar minus z2 bar. Now simplify it. It is z1 z1 bar and z1 z2 bar and minus z2 z1 bar and minus minus plus z2 z2 bar. Now we are going to simplify it. This is the mod z1 square and this is mod z2 square, and these two club and form two real z1 z2 bar. So we can easily find the property number 9 is here. Now we are going to add these property 8 and 9. We can find property number 10. It is z1 plus z2 whole square plus z1 minus z2 whole square. It is equal to twice mod z1 square plus mod z2 square, because as we know, this is mod z1 square plus mod z2 square plus 2 real z1 z2 bar, and this is equal to mod of z1 square plus mod of z2 square minus 2 real z1 z2 bar, and this is cancel out and we can easily find this is twice of z1 square and twice of z2 square. Students, similarly we can find the property number 11, az1 minus bz2 whole square plus bz1 plus az2 whole square is equal to a square plus b square times mod z1 square plus mod z2 square. Now we are going to simplify it. It is the az1 minus bz2 whole square and it is equal to az1 minus bz2 into az1 minus bz2 whole bar. Now again simplify it. It is az1 minus bz2 multiply az1 bar minus bz2 bar. Here a and b are the real number, so the conjugate of real number is also same. Now we are going to multiply it. It is a square z1 z1 bar minus ab z1 z2 bar minus ab z1 bar z2 plus b square z2 z2 bar. Now what is the value of bz1 plus az2 mod whole square? It is bz1 plus az2 multiply by bz1 plus az2 whole bar. Now again simplify it. It is bz1 plus az2 multiply with bz1 bar plus az2 bar. Simplify it. b square z1 z1 bar plus ab z1 z2 bar plus ab z1 bar z2 plus a square z2 z2 bar. Now we are going to add these two equations, and after adding we find that this is cancel out. Means if we add these two equations, left hand side is here and right hand side will be a square mod z1 square plus b square mod z2 square plus b square mod z1 square plus a square mod z2 square. Now a square is a common factor and here is mod z1 square plus mod z2 square. Similarly, b square is also common and here is mod z1 square plus mod z2 square. Now take mod z1 square plus mod z2 square as a common factor and here will be a square plus b square. This is the right hand side. So property number 11 is proved here. Students, now we are going to detailed study of the argument or amplitude of complex number z. The argument of z denoted by ARGZ or amplitude AMPZ is the angle which OP makes with the positive direction of real axis. The angle being measured in anti-clockwise sense. If z is equal to x plus iota y, then the angle theta given by tan theta is equal to y upon x is said to be the argument of z. We can represent this like argument z, amplitude z, it is equal to tan inverse y upon x, and you can write it is tan inverse imaginary part of z upon real part of z, and it is angle theta. Students, one note is important here. Argument z is not unique. If theta 1 is one value, then theta 1 plus 2k pi, where k belongs to integer, is the set of all possible values of argument z. Any two arguments of a complex number differ by 2k pi, where k belongs to integer. But the principal argument of a complex number z is that values of the argument which lies in the interval minus pi to pi. For z is equal to x plus iota y, theta is equal to tan inverse mod of y upon x, then the principal argument depend on quadrant in which the point xy lies. We are going to see here point number 1. If x is positive and y is equal to 0, means point lies on the real axis, then argument is 0. Principal argument is 0. If x is positive, y is positive, then it is the first quadrant. Let principal argument is theta. If x equal to 0 and y is greater than 0, means positive imaginary axis, then principal argument is pi by 2. If x is less than 0, y is greater than 0, this is the second quadrant, principal argument is pi minus theta. If x is less than 0, y is equal to 0, it is the negative real axis, principal argument is pi. If x is less than 0, y is less than 0, it is the third quadrant, principal argument is minus pi plus theta. If x is equal to 0 and y is less than 0, it is a negative imaginary axis, principal argument is minus pi by 2. If x is positive and y is negative, then complex number lies in the fourth quadrant and principal argument is minus theta if theta is the argument of the complex number. Students, how we can find the principal argument of a complex number z is equal to x plus iota y? Here we are going to study the basic steps. Step number 1, we have to find tan theta, which is equal to mod of y upon x, and this gives the value of theta in first quadrant. Alright, because y and x both are positive. Step 2, find the quadrant in which z lies. Means you have to find the quadrant with the help of sign of x and y coordinates. Step 3, then the argument of z will be according as z lies in the first, second and fourth quadrant given in this figure. Means argument of z will be theta. If complex number lies in the first quadrant, it is pi minus theta. If complex number lies in the second quadrant, it is theta minus pi. If complex number lies in the third quadrant, and it is minus theta if complex number lies in the fourth quadrant. Argument will be pi by 2 if complex number is purely imaginary and positive, and it is minus pi by 2 if complex number is purely imaginary and negative. For purely positive real number, argument is 0, and for purely negative real number, argument is pi.